The full speed line shows that we have extended map widths by maintaining the surge margin as far as can be ascertained by CFD numerical stability and significantly increased choke margin. The gain in overall efficiency is so significant at between 2 and 4 points that it would be fairly straightforward to gain more surge margin by profile trimming this blade. Total pressure contours indicate the location of a separation vortex coming off the suction side exducer. The strength and losses of this vortex are reduced in the optimal design. In a further optimization, one might create a rotor with splitters and a reduced diameter, which could allow greater flow control for the same swallowing capacity. Blade number and options for a splitter, including an independent splitter with all its own shape and position control parameters, can be added as inputs or constraints to Turbo Design 1 optimization. The design parameter comparison is shown here. The blade loading has changed from aft loading to constant loading at the shroud. At the hub, the loading has remained largely unchanged, except for a distinctive increase in leading edge loading. The overall blade length is shortened by 4.5 mm, and the tip width increased by 3 mm. The blade height at the inducer is fractionally reduced by 0.5 mm. The blade stacking at the trailing edge is increased to 4.25 degrees against rotation, which gives the familiar chevron to the exducer section. The blade lean at the leading edge and the maximum circumferential blade lean have both been reduced in the optimal design. This means that, for the same thickness distribution, we should see a reduction in root stresses due to centrifugal forces when the wheel is rotating. So we have improved mechanical as well as aerodynamic performance. It is very important to assess how accurate the design space surrogate model is. We must have confidence in the response surface model to correctly predict the shape of the design space. Otherwise, we would be using high-fidelity simulation in the wrong part of the design space. This slide shows a comparison between surrogate model predicted results and CFD results for the same geometry at the same conditions. We can see that the actual performance results are the same as the predicted values. In this series of videos, we have shown how realizing a set of requirements for building a machine learning system can lead to usable and efficient gains in component performance. The reactive response surface with CAE model is an ideal method for delivering optimal designs in a multi-point, multi-objective design space, integrating directly with the most popular simulation tools supplied by Cadence, ANSYS, and Siemens. And for a fraction of the total cost traditionally associated with large-scale, high-fidelity optimization studies involving complex geometry and flow interaction. This machine learning system, available right now, can be applied to compressors of all types and to all other types of turbo machinery: pumps, compressors, turbines, blowers, in any flow regime or working fluid.